So let me open lecture 2 by sharing the topics of today that I'm gonna cover today. In the first topic, I will discuss about stress analysis in connections. If you remember in lecture 1, we didn't discuss about the mechanics around pin A, pin B, and pin C, and like the complicated shape of the connections. So we're gonna discuss about it. And as I promised in previous lecture, I'm gonna tell you the concept of allowable stress and factor of safety. Then I will talk about stress on oblique plane. Like what if we consider a rod under tension, and if we consider stress acting on this oblique plane, how can you define it? So we'll discuss about it. And as a third topic, we'll talk about stress under general loading. And as a final topic, I'm gonna give you some additional discussion which is not included in your textbook. The topic is can we ignore gravity effect? So as you can see from all previous example, we haven't discussed about the gravity at all, and somehow and interestingly, like you're gonna find that the example problems and sample problems would include some sort of kilonewton range force, and we'll discuss about why your textbook writers use kilonewton for your textbook, and in that sense how and why we can ignore the gravity effect in our textbook. Okay, so let's begin from the first topic. So we'll discuss about stress analysis in connections first and move on to the factor of safety. So for the reliable design and safe design, we still need to consider more details, which is around the connections. As I told you, we didn't discuss about the details around the pin C, around the pin A, and around the pin B. We only discussed about rod AB, boom AB, and rod BC, and etc. So what about connections? So let's focus on around the connection C. Okay, first. Okay, so if you recall in previous problem, you remember that rod BC was under tension, like 50 kilonewton and 50 kilonewton. So the sentence that rod BC is under tension, like 50 kilonewton tension, is that it implies that the pin C applies 50 kilonewton load to the end of this rod BC, right? So pin BC is applying 50 kilonewton here, okay? And as a reaction, pin C will have force in opposite direction, 50 kilonewton in this way. Okay, so this is action and reaction pair in Newton's second law. No, it's the third law. Right, now let's take a look at like detailed dimension around this connection C. So if you look at the connections from textbook, it will have width of 40 millimeter here, and the diameter, if you remember, it was 25 millimeter. No, 20 millimeter, and your textbook specify that the diameter of the pin is 25 millimeter, which means that the other length should be 7.5 millimeter, 7.5 millimeter. Okay, now let's try to draw the free body diagram around this point. So let's take this imaginary chord and try to magnify here. Now what you're gonna realize is that these side surface, which is colored by yellow, it's under 50 kilonewton force, and to make a mechanical equilibrium, you can expect that these two surfaces, this purple surface, would subject 25 kilonewton forces in opposite directions, so that it can balance out the force, and there is no torque acting on this free body. Okay, now if you obtain the area of this purple surface, it has 70.5 millimeter multiplied by 20 millimeter, so that you can obtain the area, and the force acting on this one purple surface is 25 kilonewton. So you can find that the stress is 167 megapascal, and somehow this implies that actually our example problem is not a safe design. Because I told you that the allowable stress for steel is 165 megapascal, but somehow the stress in this purple um, area turns out to be larger than allowable stress. So I think it must be mistake of the textbook writers, and it sometimes happens, right? So it's okay. And if we consider like a factor of safety in later discussion, yeah, even though we made like a little bit of a mistake of designing this structure, yeah, our stress turns out to be slightly larger than the allowable stress. Still, it will be okay because we consider the factor of safety in the design. So yeah, we're gonna have discussion on factor of design, factor of safety maybe in 10 minutes. Now let's move on to the another part, which is pin C itself. So until now we worried about safety of road BC, right? What about this pin itself? Okay, this pin must be under force and stress, and we gotta worry about the safety of this pin itself, because even though road BC is intact, the pin C may be separated into two parts and the structure will be broken. Okay? So what you can see here is because you are pulling the road BC in this direction, and the pin would get forced in opposite direction like this. Okay, so if you make a magnify the view of the pin C, yeah, you can see free body diagram in this way. So out of your pin C, yeah, you're gonna have 50 kilonewton by road BC, like acting on here, and you're gonna have 50 kilonewton by the anchor that is attached to the rigid wall in opposite direction and same magnitude force. Okay, now if you focus on this yellow surface, let's consider imaginary surface. Shear stress acting on here is 50 kilonewton divided by pi r squared, which is 25 millimeter over 2 squared. It turns out to be 102 megapascal. So even though we didn't consider the tensile strengths in this chapter, we'll consider tensile strengths and allowable tensile strengths, and this must be taken into account when designing reliable structure. Okay, in addition to normal stress, we have to also account for tensile stress. But today's discussion, because we didn't have a detailed discussion on shear stress yet, yeah, we'll skip the discussion on whether our stress surpass the allowable shear stress or not. Now let's consider the connection around pin A. Okay, now how can I explain this better? Okay, let's focus on pin A first. So if we consider pin A, yeah, pin A is located here, and yeah, this is pin A. If you look at the top view, this is how your pin A look like. So this is your pin A, and inside this boom and anchor, this is your pin A. So what you can expect here is, because the boom AB is under compression, yeah, this guy is under compression, this boom will push the pin in opposite direction. So you can expect that, yeah, pin A is under like a 40 kilonewton force in opposite direction, and this anchor will push the pin like 20 kilonewton here and 20 kilonewton here. Okay, so this is what you can expect. Okay, so if you focus on this imaginary surface here and imaginary surface here, and try to draw a free body diagram, yeah, you have 20 kilonewton top of this surface. You have, if you combine 40 kilonewton and 20 kilonewton, you have total 20 kilonewton in left, at the bottom of the surface. So you can see that shear stress turns out to be 20 kilonewton over pi r squared, turns out to be 40.7 megapascal. Okay, so we can now determine the shear stress acting on this joint, this imaginary surface. Now, in addition to this shear stress, we have to also focus on normal stress acting on this cylinder. So if you take this part, and you can expect that there is 40 kilonewton acting on this part, and it's balanced by 20 kilonewton here and 20 kilonewton here. And if you take a imaginary surface here that is orthogonal to the 40 kilonewton force, and this surface, if you get the dimensions right, this is 30 millimeter and diameter is 25 millimeter, so the total cross-section area here is 30 times 25 square millimeter, and the force acting on here is 40 kilonewton. So you can see there is normal stress acting on here, and we call that as bearing stress, and the bearing stress turns out to be 53.3 megapascal. Okay, so it's like, if you consider real world, these are the complexity you have to consider, right? When you construct real building and cars and real structure that are made out of like a bolt and nut joint and connections, if you think about like a rigid body freshman physics problem, you only worry about, okay, the entire structure is on the force equilibrium and torque equilibrium, and that's it. But in real life, you have to consider the safety of not only the rod BC and rod AB, also pin A shear stress, pin B shear stress, pin C shear stress, and bearing stress, and etc. Okay, so you can see that in realistic engineering, more complexity comes out. Now let's consider boom AB. Okay, so in rod BC, we focused on we make a magnified view around this rod BC, and we worry about the safety of these points. Now what about boom AB? Boom AB is on the 40 kilonewton compression, so actually my answer is you don't need to worry about it. So suppose that you have a small structure with a hole like this, and this is under 40 kilonewton compression. Now you can imagine that this 40 kilonewton act on here and there. Now if you think about how much force would act on here and there, what you can realize is that you don't need to worry about the force except the gravity. There is no force that this yellow surface should sustain, right? Because this is on the compression. Okay, so you don't need to worry about safety of this zone and that zone and that zone and that zone, as we have done for rod BC. In rod BC, because it was under the tension, and these tapered parts should sustain that 50 kilonewton back in rod BC. But for boom AB, these parts, they are doing nothing. Okay, so actually, whether you hold the structure out over here, and even though you take out this part and make boom BC in this way, you're not gonna have any problem in sustaining that structure if you only consider static effect. Of course, if you have to consider dynamic effect, there are gonna be some vibration, and you cannot say that this is a safe structure. But if we only think about the static loading, the structure would be safe enough with this kind of shape. You don't need these parts. Okay? Now let's move on to pin B. Pin B is quite complex. So if you look at the magnified view here about the pin B, actually it's quite complex. But please take a look at your textbook in detail. But let me just tell you the final answer. So at the center of this pin B, it should sustain 50 kilonewton out of this rod BC, and these two parts, these purple part and this purple part, this is the point where they sustain 40 kilonewton out of a boom AB. Now if you consider this part and that part, these two yellow parts, they are sustaining 30 kilonewton downward external force, half and half. So these are the free body diagram for pin B. Now you have to consider first the cross section E. Then let's consider cross section G later. Okay? So if you look at cross-section E first, you have at the left of this cross-section E, you have 50 kilonewton downward force, and if you combine all other force to the right of this cross-section E, you should have 15 kilonewton here, so that it can satisfy mechanical equilibrium and you can obtain shear stress acting on cross-section E. Now regarding cross-section G, on the left of this cross-section G, you have 50 kilonewton here, you have 20 kilonewton here, so total you have 25 kilonewton. And to make a balance at the right side of this G, you should have another 25 kilonewton. So you can obtain the shear stress acting on cross-section G, which is 50.9 megapascal. Okay, so yeah, with this we considered like a full details about the safety of pin A, pin B, and pin C, and complex shape around the connections. Okay, so yeah, please, I would be happy if you understand the complexity of realistic structural design, which you should encounter for these complexities. In addition to this complexity, in later lectures, we'll consider so-called stress concentration effect, because the governing equation of stress distribution and the governing equation of electrostatic potential is quite similar. You know, when you have lightning rod at the top of your building, you're gonna have like a electric field concentration at the tip of this lightning rod, and that's why you're gonna have lightning acting on the tip of the lightning rod in the building. So it's the same here. Like when you have like a hole in your structure and try to pull it up, yeah, you're gonna have stress concentration here and stress concentration here. You know, and you know, the mathematics is similar to electric field concentration. Yeah, so yeah, we'll have to account for this stress concentration effect, and the problem gets even more complex. However, for now, for lecture 2, let's forget about stress concentration effect, and let's only talk about the average stress acting on the entire plane. Okay, so let me give you a lecture on stress concentration in later lectures. Now, let's have a brief discussion about factor of safety as the final topic of this video clip. So suppose that you are measuring the material property by doing tension experiments, and if you have the area A and force P, and if you draw stress and strain relationship, this is what you're gonna get for typical brittle material, yeah, such as like a glass. Okay, if you do like experiments on erasers or steel or copper, you're gonna have some sort of this extension, but for glass you're gonna have sudden and catastrophic failure at the top of this point. Okay, and we call this as ultimate stress at failure and sigma u, typically noted as sigma u. However, in structural design, we don't set sigma allowable is the same as sigma u, because this is, I would say, too dangerous. The reason is following. So when we do typical statics analysis, we don't account for dynamic effect. Okay, we typically considers statics effect only. However, in realistic structure and bridges and buildings and cars, it should be under dynamic loading, and the effect of dynamic loading is quite immense. Suppose that you are on top of the weighing machine. So on top of weighing machine, suppose that you are 80 kilogram. Yeah, if you stand still, you're gonna have 80 kilogram reading at your feet. However, if you keep moving your arms, and if you keep moving your knees, you're gonna have a weight even more than 80 kilogram. It can be 100 kilogram depending on the acceleration you are giving. Okay, so there must be some safety margin when designing the building. Okay, so safety under steering loading is not enough. So typically we define sigma u over sigma al allowable stress as a factor of safety. If factor of safety is 1, you can make really light structure. However, there is no margin on any human error and any dynamic loading. However, if you define a factor of safety much larger than 1, it will be very reliable, but it will be very heavy. So most ancient buildings, such as huge buildings in like Greece and Roman buildings, you see like really thick stones and very tiny window zone. Yeah, the reason is they didn't have the concept of vector of safety, and they didn't measure the material property correctly back in older days. So what they have to do is, by some human intuition, they set the vector of safety really larger than 1, so that they have good factor of safety, even though they forget and they give up the lightness of the building. So typically the factor of safety you're gonna see in our textbook will be around 1.5 and 2, and yeah, that should be enough for most of the example problem that we're gonna consider. Okay, so yeah, please remember that allowable stress typically set as a value similar than the ultimate strength, because there can be human error, there can be dynamic effect, there can be mistakes in measuring a material property. So typically the maximum stress allowed for your structure is set as a smaller value than ultimate strength of the material, and that's the message you have to remember from factor of safety discussion.